Okay, hello and welcome back to Chemistry Talk. Today we will be continuing our discussion of thermochemistry, and we're going to cover one of the more challenging topics in thermochemistry, and that is the phase change and the phase diagram. And the calculations that come with these phase change calculations can be pretty tricky. So let's begin. So what is a phase diagram? Well, a phase diagram is showing us the conversion of a substance, any substance, water, ethanol, some substance, and it's going from a solid to a liquid to a gas. So there's three phase changes. So in a phase diagram, you're going from a solid to a liquid to a gas. So here we have some substance. It's starting off as a solid here. And then what happens? Well, it gets into this phase where the temperature is constant. The temperature is no longer changing. You see the y-axis is temperature. So here there is some delta T. Then it gets to this phase where it's really a solid and a liquid at once, and the temperature is constant. Then what happens? Then it goes into a full liquid. You have some delta T here, once again. We have a change in temperature, so there is some delta T. And then what? Then it's back into this, change the color. Then it's back into this multi-part phase. It's a liquid and a gas at the same time. Temperature is constant, so no change in temperature. And then finally, we're straight into a gas. And that is the end of the phase change. So all phase changes occur in this same fashion, solid to liquid to gas. However, you can be going the opposite direction, from a gas to a liquid to a solid. So when you are going from left to right, these changes that are occurring are endothermic, meaning the value for heat is positive. We're adding heat to accomplish these phase changes. So if we're going from a solid to a gas or a solid to a liquid, we are having a positive Q, an endothermic change. The opposite is going from a gas to a solid. For that, Q is negative. We are releasing heat. The changes are exothermic. Now, what's interesting is that in these purplish lines, there is a constant state of matter. So here it would be a solid, here it would be a liquid, here it would be a gas. But in between where these two blue lines are, it's a mixture of states. You're kind of in a solid and a liquid. So to calculate the heat in these blue line areas, you need molar enthalpies. And there's four of them. The first one is called the heat of fusion, and it's represented by delta H with a little fusion there. And that is the same thing as melting. So it is an endothermic change. It's a positive Q. It's the same thing as melting. So that would be right here. The heat of fusion is melting. The opposite would be freezing, but we don't call it that. We call it the heat of solidification. It's going to a solid, and that's the same thing as saying freezing or solidifying. So this would be an exothermic change. Q is negative, and melting would be an endothermic change. Q is positive. Okay, we have two more in this liquid gas area. We have the heat of vaporization. We represent that as vapor, heat of vaporization. That is a liquid going to a gas, so it's vaporizing. Therefore, the heat of vaporization. Sometimes this is called the boiling point or the heat of boiling, but I usually say the heat of vaporization. Here, Q is a positive value. We're going from a liquid to a gas. The opposite, the heat of condensation. We're condensing the gas into a liquid. We're going the opposite direction. If we're going in the opposite direction, Q will be negative. It's an exothermic change. This point here is the boiling point of the substance. This point here is the melting point of the substance and the freezing point. So this is your phase change. Okay, endothermic changes. We are going up the stair step to the right. Q is positive value. You're increasing the temperature of the solid. That would be the heat of fusion. You're melting it. Increasing the temperature of a liquid, well, you're going to boil that liquid. Could be the heat of evaporation, also known as the heat of vaporization, which is what I tend to call it more. You're vaporizing the liquid into a gas. So heat of evaporation, heat of vaporization, endothermic changes. The opposite, you're going down the stair step to the left. Q is negative. It's exothermic. That would be the heat of condensation. You're condensing a gas into a liquid, right to left. Freezing, the heat of solidification. You're taking a liquid and you're putting it back into the solid state. Q is negative. So enthalpy changes come in pairs. So this is our first pair that occurs right here. Call that pair 1. And our second pair occurs here. Now here I gave you fusion and solidification, but the second pair here is the heat of vaporization and the heat of condensation. That's our second pair. And our first pair I gave you here, it's the heat of fusion and the heat of solidification. So what I'm demonstrating here to the left is that these changes have the same value. When we're melting water, we're releasing or absorbing 6.02 kilojoules of heat. It's an endothermic change. The opposite, we're coming from the left now. We're solidifying the water into ice. That's a negative value for enthalpy. We're releasing heat. So these have the same number, but they're different in magnitude. So if you were given the heat of solidification and you needed the heat of fusion, you would just switch the signs. Same here for ethanol. we're given the heat of fusion, melting. We're absorbing 5.01 kilojoules of heat, but when we're solidifying ethanol, the opposite direction, we're releasing negative 5.01 kilojoules of heat. So it's the same number, just different values and sign. So there's two other changes that we could talk about. The first one being sublimation. This is when you go straight from a solid to a vapor or a gas. That's a positive value. We're going from left to right. We're absorbing heat. Deposition is the exact opposite. We're going from a gas or a vapor to a solid. We're releasing heat. Q, or the value for heat, is negative. Here, whoops, shouldn't be a G. Q is positive. We're absorbing heat. Okay, so I have two examples here. These are typical problems that you will see. The calculations are a little bit involved, so I have an extra page where I'll be doing most of the calculations. How much heat would it take to convert 10 grams of ice at negative 10 degrees Celsius to steam at 110 Celsius, given the following information? So we're given various information. I'm not sure if we'll need all of this, but we are given specific heats of liquid water, ice, and steam, the melting and boiling point of water, and some molar heat of fusion and vaporization. So what I like to do first is draw the phase changes that are occurring. And that will help us to determine which heat we're going to need. So the problem says that we're converting ice to steam. That means we're going from a solid to a gas or a vapor. So we're going to have 5 Qs. 1 Q here, 1 Q here, 1 Q here, 1 Q here, and 1 Q here. 5 Qs. Let's give them the information we're given. Well, I know that the boiling point of water occurs right here. The melting point of water occurs right here. And that's at 0 degrees Celsius. What else do I know? I know that the boiling point occurs right here. And that's 100 C for water. But if you notice, we're starting at negative 10 degrees Celsius. So we're actually starting below the melting point, which means that it's a solid, and that makes sense because it's solid ice. And we're converting it to steam. That's above the boiling point at 110 degrees Celsius. Okay. Let's look at our Qs. We have 5 of them. 1 Q here, we're going from a solid to a liquid. 1 Q here, we're between a solid and liquid phase. 1 Q here, we are a liquid at this point. 1 Q here, our 4th Q, we're between a liquid and a gas. And our 5th Q here. So 5 Qs. If you recall, in between these Q2 and Q4, we need to use the molar enthalpies because there is no change in temperature. So let's see, we're given the heat of fusion, that's good, we need that. That's melting. And that is an endothermic change, and that's what's going on here. So we're going to need the heat of fusion. And we should have the heat of vaporization, yes we do. and this point is the heat of vaporization. So we're going to need those changes. Looks like we're going to need almost all the information here. So let's write out our Q's, and then we'll solve for them. What we can do is find each Q value, add them up, and that is how much heat it would take. Q1, well, we have a temperature change. So it would be your typical mass times specific heat times delta T. Q2 is an enthalpy change. It would just be the mass of ice times the heat of fusion. Q3, we have another temperature change, a delta T. So it would be mass times specific heat times delta T. Q4, we have an enthalpy change, the mass times the heat of vaporization. No change in temperature, so we have to use the enthalpy change. And finally, Q5, we do have a change in temperature, so it would be the mass times specific heat times delta T. Q total, which is what we're looking for, will be the sum of our 5 Q's. So if you mess up on one of the Q's, then your answer will be wrong. So you got to be really careful here. All of our Q's should be positive. Why? Because we're going up the stair step. We're converting an endothermic phase change. So if our Q is negative, something's wrong. It should be positive because this is an endothermic change. So what I'm going to do is I'm going to solve for all these 5 Q's on this page here. So our first Q, Q1, we have a temperature change. So it would be mass times specific heat times the change in temperature. Our mass of ice is 10 grams. The specific heat of ice, make sure you're using the right specific heat, is 2.06. The change in temperature, delta T, would be 0 minus negative 10, or just 10. So Q1 comes out to be 206 joules. So all of our answers should be in joules. Q1. Q2. Oh, remember, this is the heat of fusion. Whoops, this is the heat of fusion. We are in between a solid and a liquid. So it's the mass of ice times the heat of fusion. What is the heat of fusion? Well, the heat of fusion right here is 6.02 kilojoules per mole. So a little alarm bell should be going off in your head here because we have a problem. We're given the heat of fusion in kilojoules, but our Q's are in joules. So we need to convert the molar heat of fusion into joules. The best way to do that is dimensional analysis, starting off with your ice. So we have 10 grams of ice, or water. 1 mole of water, or ice, is approximately 18 grams. Now we're going to use the heat of fusion. 1 mole of water. The heat of fusion is 6.0, 2 kilojoules. How many kilojoules in a joule? There is 1 kilojoule per 1,000 joules. So our final answer is in joules. Grams cancel, moles cancel, kilojoules cancel. Q2 equals 3,344 joules. Fix that 3. So be careful with the units here. If we didn't do that change, then we would have gotten the wrong answer. It needs to be in joules. Okay, next, Q3. Well, we have a temperature change here. Now we're right here. Q3 equals the mass times specific heat times delta T. We are a liquid now, so we're still 10 grams. We need to use the specific heat of liquid water, 4.18. Our change in temperature, 100. We're starting at 0 going to 100, so the change in temperature is 100 degrees Celsius.
It's 11 o'clock.
So Q3 comes out to be 4,180 joules. Big numbers, but all is good. So that's Q3. Notice that all our Q's are positive. It should be that way because it's an endothermic change. Q4. Well, we have no change in temperature. We just have the heat of vaporization. So Q4 equals the mass of ice times the heat of vaporization. Now let's see what units we were given the heat of vaporization. 40.6 kilojoules per mole. No good. We need it in joules. So we're going to have to do a little bit of dimensional analysis, just like we did for the heat of fusion. 10 grams of ice, 1 mole of ice or water, 18 grams. To convert 1 mole of water to a gas, we need 40.6 kilojoules. And 1 kilojoule is 1,000 joules. So Q4 equals 22,556 joules. Positive value, grams cancel, moles cancel, kilojoules cancel, left with joules. All right, almost there. See, these problems take a while, so you got to be careful. Q5, our final temperature change, we're going to a gas, mass times specific heat times delta T. Mass of ice, 10 grams. We need the specific heat of steam, because we're now in a gas, 2.03. Change in temperature, 10 degrees. 10 degrees Celsius. Fix that. Change in temperature is 10 degrees Celsius. So Q5 equals 203 joules. All positive values for Q. So finally, what's Q total? It would be the sum of all our Q's. 206 for Q1, 3,344 for Q2, 4,180 for Q3, 22,556 for Q4, and 203 for Q5. So Q total, or QT, equals 30,489 joules. And that is our final answer. So it takes 30,489 joules to convert 10 grams of ice to steam. Final answer. Okay, one more example here. Calculate the heat released when 100 mils of ethanol cools from 100 degrees C to 0 C. So cools, we're going the opposite direction. This change is going to be exothermic, so Q is going to be negative. So let's draw out what we know from our phase diagram. We're starting at 100 degrees C. The boiling point of ethanol, 78.3, given to us on the left. The melting point of ethanol, negative 114 C. The question asks when it cools from 100 to 0 C. So 0 must be somewhere in between here. So we only will have 3 Qs. 1 Q here, 1 Q here, and the other Q here. So 1, 2, 3. Here it's a liquid, here it's a liquid, and a gas, but mostly liquid, and here it's a gas. Q1 will equal mass times the specific heat times delta T. We have a change in temperature. Q2 will equal the mass times the heat of condensation. We're going from a gas to a liquid. Heat of condensation. And Q3 will be another temperature change, or cooling. Mass times specific heat times delta T. So let's solve for Q1 first. Q1, we have a temperature change, mass, times specific heat, times delta T. How much of ethanol do we have? Well, we have 100 milliliters of ethanol. So we can use the density of ethanol to convert it to grams. 1 mil of ethanol, 0.79 grams. So we have 79 grams. 79 grams of ethanol. So our mass for Q1, 79. Specific heat, the vapor, we're in a gas. So 1.2. Change in temperature. Final temperature 78.3. Initial temperature 100 C. So we have a change in temperature of negative 21.7 C. Q1 equals negative 2,057 joules. And it's good that it's negative because it's an exothermic change. Q2, we're in enthalpy change. It's the mass times the heat of condensation. Temperature is constant, so no change in temperature. Wait a minute, we're not given the heat of condensation, but what do you know? You know that the heat of vaporization is the opposite of the heat of condensation. So the heat of condensation would be the negative value of the heat of vaporization. So it would be negative 38.72 kilojoules per mole. So heat of condensation equals negative 38.72 kilojoules per mole. Once again, we have another problem. We need our answer in joules. This is in kilojoules. So we're going to do dimensional analysis to get the grams of ethanol into joules. 79 grams of ethanol we have. 1 mole of ethanol let's see. We have 2 moles of carbon, 5 moles of hydrogen, 1 mole of oxygen, and another mole of hydrogen. So that's 46 grams for a molar mass of ethanol. 1 mole, 46 grams. It takes 1 mole of ethanol to cool into a liquid, and it uses negative 38.72 kilojoules of heat. One kilojoule, 1,000 joules. Q2 equals negative 66,497 joules. One more Q, Q3, or I guess Q1, whatever you want to call it. Q3 would equal the mass times the specific heat times delta T. I'm going to change these here to reflect so we don't all get confused. So this was Q1, Q2, Q3. This is Q3, Q2, Q1. Just did it the opposite way. So Q3 equals mass times specific heat times delta T. The mass of ethanol, 79 grams. The specific heat of liquid ethanol, 2.45. The change in temperature of ethanol, 0 minus 78.3, because we're right here in this little area. So negative 78.3 degrees Celsius. So Q3 equals negative 15,155 joules. So Q total would equal Q1, negative 2,057 joules, plus Q2, negative 66,497 joules, plus Q3, negative 15,155 joules. So Q total equals negative 83,709 joules. And that's our final answer. Whoops, that should say joules. And that is our final answer, negative 83,000. Notice it's negative because the change is exothermic. And that's Q total. So that is how much heat it takes to cool 100 mils of ethanol to 0 degrees Celsius. I hope this video helped you to understand phase changes. Tricky topic, but I hope this helps. And we'll continue our discussion of thermochemistry in our next video. Thank you very much.